Distribution of mutual information. Marcus Hutter, IDSEA Laria, CH6928, Mano Lugano, Switzerland. Marcus at idesi.ch. Abstract. The mutual information of two random variables z and j with joint probability is commonly used in learning Bayesian nets as well as in many other fields. The chances 7rij are usually estimated by the empirical sampling frequency nij, leading to a point estimate j nij in for the mutual information. To answer questions like, is j nij in consistent with 0? Or what is the probability that the true mutual information is much larger than the point estimate? One has to go beyond the point estimate. In the Bayesian framework, one can answer these questions by utilizing a prior distribution P7R comprising prior information about 7R. From the prior P7R, one can compute the posterior P7ln, from which the distribution PILN of the mutual information can be calculated. We derive reliable and quickly computable approximations for PILN. We concentrate on the mean, variance, skewness, and kurtosis, and non-informative priors. For the mean, we also give an exact expression. Numerical issues in the range of validity are discussed. Introduction. The mutual information J, also called cross-entropy, is a widely used information theoretic measure for the stochastic dependency of random variables. It is used, for instance, in learning Bayesian nets, where stochastically dependent nodes shall be connected. The mutual information defined in can be computed if the joint probabilities 7rij of the two random variables z and j are known. The standard procedure in the common case of unknown chances 7rij is to use the sample frequency estimates nij instead, as if they were precisely known probabilities. But this is not always appropriate. Furthermore, the point estimate j nij gives no clue about the reliability of the value if the sample size n is finite. For instance, for independent z and j, 7r equals 0, but j nij equals o n minus 1/2 due to noise in the data. The criterion for judging dependency is how many standard deviations j nij is away from 0. In the probability that the true j7r is greater than a given threshold has been used to construct Bayesian nets. In the Bayesian framework, one can answer these questions by utilizing a prior distribution p up 7r. Prior distribution p pi, which takes account of any impreciseness about pi. From the prior p pi, one can compute the posterior p pi n, from which the distribution PIN of the mutual information can be obtained. The objective of this work is to derive reliable and quickly computable analytical expressions for Pn. Section 2 introduces the mutual information distribution. Section 3 discusses some results in advance before delving into the derivation. Since the central limit theorem ensures that PIN converges to a Gaussian distribution, a good starting point is to compute the mean and variance of PIN. In Section 4, we relate the mean and variance to the covariance structure of P pi n. Most non-informative priors lead to a Dirichlet posterior. An exact expression for the mean, Section 6, and approximate expressions for the variance, Section 5, are given for the Dirichlet distribution. More accurate estimates of the variance and higher central moments are derived in Section 7, which lead to good approximations of PIN, even for small sample sizes. We show that the expressions obtained by heuristic numerical methods are incorrect. Numerical issues and the range of validity are briefly discussed in Section 8. We consider discrete random variables ZE1, R, S, and an IID random process with samples IJ, E1, R, X1, S, drawn with joint probability pi ij. An important measure of the stochastic dependence of Z and J is the mutual information. The natural logarithm and pi I plus equals j pi ij and pi plus j I pi j are marginal probabilities. Often one does not know the probabilities pi ij exactly, but one has a sample set with an ij outcomes of pair ij. The frequency pi ij equal nj may be used as a first estimate of the unknown probabilities. N equals psi j nij is the total sample size. This leads to a point frequency estimate I equals I j nij log nij nj for the mutual information per sample. Unfortunately, the point estimation I pi gives no information about its accuracy. In the Bayesian approach to this problem, one assumes a prior second-order probability density p pi for the unknown probabilities pi ij on the probability simplex. From this, one can compute the posterior distribution p pi n, p pi ri pi j. The ninja are multinomially distributed. This allows to compute the posterior probability density of the mutual information. PIN equals av pi p n pi. The Github distribution restricts the integral to for which p equals I. For large I, b denotes the mutual information for the specific chances pi, whereas I in the context above is just some non-negative real number. I will also denote the mutual information random variable in the expectation EI and variance var I. Expectations are always WR to the posterior distribution Pn. Since pi Imax with a sharp upper bound Imax equals min log R log S, the integral may be restricted to Imax, which shows that the domain of PIN is 0 Imax. Pi size n equals 100, PILN is strongly peaked around p pi and PLN gets strongly peaked around the frequency estimate I equals I pi. The mean EI equals PLN DI equals I PLN D pi, and the variance var I equals I minus sword equals EI minus EI squared chord are of central interest. Results for I under the Dirichlet prior. Most non-informative priors for p pi lead to a Dirichlet posterior distribution I to n minus 1 t t t t h b p pi n x ij pi w r pre a I on nij nij plus nij, where nij are e number of samples ij, and ni plus j comprises prior information, 1 for the uniform prior, ch for Jeffrey's prior, 0 for Haldane's prior, ch for Perk's prior. In principle, this allows to compute the posterior density PLN of the mutual information. In sections 4 and 5, we expand the mean and variance in terms of n-sol, EJI, nij plus 1, rmi plus 1 on f plus 1, 8 minus 1 o n squared var I. The first term for the mean is just the point estimate I pi. The second term is a small correction if n are 8. Kleider determined the correction by Monte Carlo studies as min t quadrivornon 841. This is wrong unless 8 or rare 2. The expression 2EEIN they determined for the variance has a completely different structure than ours. Note that the mean is lower bounded by constant plus O n inner squared, which is strictly positive for large but finite sample sizes, even if Z and J are statistically independent and independence is perfectly represented in the data, I pi equals 0. On the other hand, in this case, the standard deviation equals y EI correctly indicates that the mean is still consistent with 0. Our approximations for the mean and variance are good if T8 is small. The central limit theorem ensures that PL converges to a Gaussian distribution with a mean EI and variance var I. Since I is non-negative, it is more appropriate to approximate P2 pi as a gamma, scaled Heath-War, or log-normal distribution with mean EI and variance var I, which is of course also asymptotically correct. A systematic expansion in n-min of the mean, variance, and higher moments is possible but gets arbitrarily cumbersome. The OM square U terms for the variance and leading order terms for the skewness and kurtosis are given in section 7. For the mean, it is possible to give an exact expression EI t equals minus that nij ij 1jj plus 1 minus 1jj n plus j n plus 1 with 1jj n plus 1 equals dinij ni equals log n plus log ups for integer n. See section 6 for details and more general expressions for non-integer arguments. There may be other prior information available which cannot be comprised in a Dirichlet distribution. In this general case, the mean and variance of I can still be advocated by the entropic prior PFPXEH pi, related to the covariance structure of P7 felon, which will be done in the following section. Approximation of expectation and variance of I. In the following, let phi j be the expected value of 7Fij. Since P of 7FLN is strongly peaked around 7F equals FR for large N, we may expand J7F around FR in the integrals for the mean and the variance. With Iij equals 7Fij minus Farij and using Lij 7Fij equals Lifrij, we get for the expansion of J7F equal JFR, plus 2 log Iij plus taking the expectation the linear term Eijz drops out. The quadratic terms Eij7Ij, 7FKL are the covariance of 7F under distribution P 7FLN and are proportional to n as 1. It can be shown that Ei3 equals n minus 2. The Kronecker delta by is 1 for I equals j and 0 otherwise. The variance of j in leading order in n minus 1 is where it converges up to terms of order n is 2. So the leading order variance and the leading and next to leading order mean of the mutual information JF7F can be expressed in terms of the covariance of 7F under the posterior distribution P of 7FLN. The second-order Dirichlet distribution. Non-informative priors for P of 7F are commonly used if no additional prior information is available. Many non-informative choices lead to a Dirichlet posterior distribution, where R is the gamma function, and Nij equals Ni plus Nj, where Ni are the number of samples Ij, and Nj comprises prior information, 1 for the uniform prior, for Jeffrey's prior, A for Haldane's prior, minus S for Perk's prior. Mean and covariance of P up 7n are AE Nij phi j gov minus n. Inserting this into, we get after some algebra for the mean and variance of the mutual information I7R up to terms of order n-2. Eij 8 minus 1 O minus 2 plus 2n plus 1 var I touch a 1 at kj2 plus on minus 2 j and k and lmpq defined later depend on 7rij i.e. are O1 and n. Strictly speaking, we should expand n jofzelds plus on minus 2, i.e. drop the plus 1, but the exact expression for the covariance suggests keeping the plus 1. We compared both versions with the exact values for various parameters 7r. In most cases, the expansion in n tau L was more accurate, so we suggest using this variant. Exact value for EI, it is possible to get an exact expression for the mean mutual information EI under the Dirichlet distribution. By noting that x log x equals dx does I6 equal L, x equals 7r plus 7r plus j, one can replace the logarithms in the last expression by powers. From we see that EI 7r6 equals da I j. Taking the derivative and setting 8 equals 1, we get d1 e 7rij log 7rj equals d equals 7 of 6, 6 1 equals 2, nij 1j 1j nij plus 1j n plus 1. The 1j function has the following properties. See S84 for details. D log fz f of z 1 1 1j of z equals fz prime equals log z plus 2z minus 12z tour 1j n 1j range equals l of j n plus 1 2 log 2 plus 2l 2k minus 1. The value of the Euler constant is irrelevant here since it cancels out. Since the marginal distributions of 7ri plus and 7r plus j are also Dirichlet with parameters ni plus and n plus j, we get similarly 1 as ln plus j 1j minus 1 as 1 j1 n plus 1. Inserting this into and rearranging terms, we get the exact expression 4ei equal to minus lnij plus 1 minus 1j ni plus 1 is 1 n plus 1. For large sample sizes, ij z plus 1 approaches logs and equation 15 approaches the frequency estimate I7r. Inserting the expansion ijz plus 1 equals log z plus 2 into equation 15, we also get the correction term rms plus 1 of 3. The presented method may also be used to determine an exact expression for the variance of I7f. All but one term can be expressed in terms of gamma functions. The final result, after differentiating with respect to 31 and 32, can be represented in terms of ij, and its derivative ij. The mixed term E7 of I plus 1 7f plus j2 is more complicated and involves confluent hypergeometric functions, which limits its practical use. Generalizations. A systematic expansion of all moments of PILN to arbitrary order in n-1 is possible, but gets quite cumbersome quickly. For the mean, an exact expression was already provided 15, so the focus here is on the variance, skewness, and kurtosis of PILN. The third and fourth central moments of 7f under the Dirichlet distribution are as follows. 27 RB 7 RC 7 RA 7 RBC minus RB 7 RC 5 7 RC 7 to 5B plus 7 RAC 5 AB 5 BC on RD 7 RB 7 RJ RCD a C5 AB minus A7 RB JRD A7 RC 5 5 5D minus 7 FD 7 FD F7 FC 5 B 7 FNFC 7 FBC 5 BD B 7 FCC 5 CD plus 7 RS 7 RC 5 AB 5 CD plus 7 RBCC 5 BD plus 7 RS 7 RBC 5 D 5 BC plus O and A equals IJ, B equals KL, E1 RX 1 8 being double indices, C5AB equals C5 K C5 JL, 7 RIJ. Expanding D, K equals 7F minus 7RK and ED leads to expressions containing E7 SMFB, which can be computed by a case analysis of all combinations of equal unequal indices A, B, C using 8. Many terms cancel leading to the above expressions. They allow to compute the order n-2 term of the variance of 7F. Again, inspection of 16 suggests to expand in n plus L n plus 2 minus 1 rather than in m-2. The variance in leading and next to leading order is var I k minus j2 plus var 8 minus 1 ch minus 1 q plus o minus 3 n plus 1 n plus L n plus 2. ml minus 1 plus nij log n ij ni plus jn ni plus a q nij ni plus n plus jj and k in 12 and 13. Note that the first term also contains second-order terms when expanded in n-1. The leading order terms for the third and fourth central moments of PLN are nij I ni n minus all j n ni plus n plus j, from which the skewness and kurtosis can be obtained by dividing by var I 3/2 and var I square if respectively. One can see that the skewness is of order n square minus 1/2 and the kurtosis is 3 plus o n minus 1. Significant deviation of the skewness from A or the kurtosis from 3 would indicate a non-Gaussian I. They can be used to get an improved approximation for PIN by making, for instance, an ansatz and fitting the parameters B, C, J, J, and J to the mean, variance, skewness, and kurtosis expressions above. P0 is the normal or gamma distribution, or any other distribution with a Gaussian limit. From this, quantiles PIIN can be computed. A systematic expansion of arbitrarily high moments to arbitrarily high order in N1 leads, in principle, to arbitrarily accurate estimates. Numerics, there are short and fast implementations of IF. The code of the gamma function in can be modified to compute the IF function. For integer and half-integer values, one may create a lookup table from in. The needed quantities j, k, l, m, and q, depending on n, involve a double sum, p only a single sum, and the r plus s quantities j plus and j plus j also only a single sum. Hence, the computation time for the central moments is of the same order ORS as for the point estimate. Exact. Values have been obtained for representative choices of 7Rij, Rs, and n by Monte Carlo simulation. The 7Rij equals ij x plus are Dirichlet distributed, if each xij follows a gamma distribution. See how to sample from a gamma distribution. The variance has been expanded in TS, so the relative error var IAP is of the approximation and are of the order of TS and var I exact n, TS squared respectively if z and j are dependent. If they are independent, the leading term drops itself down to order n²-2, resulting in a reduced relative accuracy OTIS. Of comparison with the Monte Carlo values confirmed an accuracy in the range TS1.2, the mean is exact. Together with the skewness and kurtosis, we have a good description for the distribution of the mutual information PIN for not too small sample bin sizes Nij. We want to conclude with some notes on useful accuracy. The hypothetical prior sample sizes n ta j equals a mat s talt doth 1 can all be argued to be non-informative. Since the central moments are expansions in n-1, the next to leading order term can be freely adjusted by adjusting nj e0, 1. So one may argue that anything beyond the leading order is free to will, and the leading order terms may be regarded as accurate as we can specify our prior knowledge. On the other hand, exact expressions have the advantage of being safe against cancellations. For instance, the leading order of EI and EI squared does not suffice to compute the leading order of var I. Acknowledgements. I want to thank Ivo Qui for valuable discussions and Marco Zafalon for encouraging me to investigate this topic. This work was supported by a CNF grant 2000-61847.0 to Jürgen Schmidhuber. References M. Abramowitz and I. A. Stegen, editors. Handbook of Mathematical Functions. Dover Publications, Inc., 1974. M. Brand, Structure Learning in Conditional Probability Models via an Entropic Prior and Parameter Extinction. Neural Computation, 11.5-1155-182, 1999. W. Bunting, A Guide to the Literature on Learning Probabilistic Networks from Data. IEEE Transactions on Knowledge and Data Engineering, 8-19510, 1996. T. M. Cover and J. A. Thomas, Elements of Information Theory. Wiley Series in Telecommunications, John Wiley & Sons, New York, NY, USA, 1991. A. Gelman, J. B. Carlin, H. S. Stern, and D. B. Rubin, Bayesian Data Analysis. Chapman, 1995. D. Heckerman, A Tutorial on Learning with Bayesian Networks. Learning in Graphical Models, pages 301 to 354, 1998. G. D. Kleider and R. Jarusek, Learning Bayesian Networks Under the Control of Mutual Information. Proceedings of the 6th International Conference on Information Processing and Management of Uncertainty in Knowledge-Based Systems, IP 1996, pages 985 to 990, 1996. G. D. Kleider, The Posterior Probability of Bayes Nets with Strong Dependencies. Soft Computing, 3162-73, 1999. W. H. Press, B. P. Flannery, S. A. Kolsky, and W. T. Vetterling. Numerical Recipes in C, The Art of Scientific Computing. Cambridge University Press, Cambridge, 2nd edition, 1992. E. S. Sufi, Principal Information Theoretic Approaches, Journal of the American Statistical Association, 95, 1349-353, 2000. D.R. Wolf and D. H. Wolpert. Estimating Functions of Distributions from a Finite Set of Samples, Part 2, Bayes Estimators for Mutual Information, Chi-squared Covariance and Other Statistics. Technical Report, LAUR 9833, Los Alamos National Laboratory, 1993. Also Santa Fe Institute Report, SFI TR 93-7047.